Alright, so our popple comes from a company called Shaw, which is a manufacturer of flooring, and it comes from one of their hardwood plants. So when processing hardwood flooring, defects in the wood result in irregular length boards, which leads to difficulty in efficient packing of them for shipping. This issue is addressed by implementing what is called cut fill. And cut fill is a rule for subdividing the boards left after removing the defects from the wood into convenient lengths. Our goal is to define a cut fill which requires a minimum number of cuts while still achieving efficient packing. So we're going to define a cut fill. And a cut fill is a set of closed real intervals which contains allowable lengths. So allowable length is a length that is in the cut fill, which is what our boards are allowed to be. And then a non-allowable length is one that is not in the cut fill, which is a length that our hardwood boards are not allowed to be. Okay. So when a defect is found, it is cut out by the saw, which leaves us with these pieces of boards that are just like random lengths. So we're going to look at an example of a cut fill. This is actually their real cut fill. These are the intervals that they use for their saw to cut their wood into pieces, which is the lengths they're allowed to be. And we're going to look at just a small example. So we have a hardwood board, and it's 58 inches long altogether, and we're going to let this piece right here be the defective piece. Okay, so the defect starts here, ends there. It's a 14-inch piece. And what happens is the saw sees that, someone makes marks, they see that, and it cuts it out, and then we are left with just two pieces of random lengths. So we have a 12-inch piece and a 32-inch piece. So what happens to the 12-inch piece? The 12-inch piece lives inside that first interval, and so it's allowed, and it just goes through processing. The 32-inch piece is the problem, though, because 32 doesn't live in either one of these intervals. So we have to do something about that. We have to keep three things in mind whenever we cut it into pieces. We have to think about what the cut fill actually is. We want to subdivide the board such that we have the longest piece we can possibly get out of it while keeping the remainder also in the cut fill. So whenever we take this board and we cut it, we want to be able to use both pieces. That's the point. So first you're going to try and remove like the smallest bit there, the 10.75. Take that out first, because that will give you the biggest piece you can possibly have. And you want to see if that is also in the cut fill. So in this case, with our 32-inch board, that happens, right? We take the 10.75 out, and the 21.25 is actually in the first interval as well. And so we've taken that board, we've taken it from being a non-allowable length to two pieces that are allowable lengths, where one of them is as big as we can possibly make it. So when we think about the distribution of the defects, we decided that it would follow an approximate Poisson process, but it couldn't be exactly Poisson because that allows for you to have zero, right? Whenever you do a Poisson distribution, you have a possibility of having a value of zero, and, right, yep. And so we had to change it to account for that because we are only dealing with defective boards, so we're guaranteed to have at least one defect per board. So we get rid of the zeros using a zero truncated Poisson distribution. Removes the possibility of it having value of zero, and that gives us a conditional probability, right? So we have the probability that x equals this given that x is greater than zero. And so we can scale that to any interval along our length of board and determine if a defect lives there or not. So if we want to find out if there's one centered in this bit here, like a smaller piece, as opposed to like a bigger piece, we can do that. We just have to scale it. So now we're going to talk about the process that the boards actually go through. The boards are sorted into defective and non-defective pieces. We don't care about the non-defective pieces, so just go to boxes. We're concerned with the defective boards. It goes to where a human person looks at it and takes markers and marks on the sides of the defects for the saw to read that and be able to know where to cut. They take this big yellow marker and just make marks on either side. And then the saw sees it, the defect saw, and it cuts it out, and then it implements the cut fill. It takes those pieces like we saw and decides where cuts need to be made. Then from there it goes to what's called a profiling machine, which profiles the boards, right? Whenever we cut it, it'll be like flat, right? But they actually need to have tongues and grooves, like this would be your tongue and there's your groove, and they stick into each other like puzzle pieces whenever you're installing hardwood floors. So they have to do that. That takes off a little bit more off of your wood. And then from there, it goes to what's called the nester, which scans the lengths and decides where and how to match the boards together for packing. We'll get back to that in a minute. And then from there, it goes into the box. So why would changing the cut bill matter? Like, why would we care and want to do that? And how would that help us influence the yield? All right, so why do we care about cut bill? Every time we cut board, a width of the blade, which is called a kerf, is lost, right? You have wood, you cut it, it doesn't make it perfect, right? It takes off a little bit of length. So every time a cut is made, we lose some wood. And every time a cut is made, we also have to reprofile both ends, which takes off even a little bit more. And so all of that's turned into sawdust and we can't get it back, right? So if we can minimize the number of cuts, then we can reduce the amount of waste in the long run. It's a little bit for one board, but over time, right, that's going to build up and be a lot of waste. Right, so overall, our task is to optimize the yield from these defective boards by setting a cut bill, which will efficiently match them for packing while lowering the average number of cuts and therefore minimizing waste.
All right, so for our approach, we have created a model to simulate their manufacturing process. The simulation has given us the flexibility to, 1, make modifications to fit the manufacturer's actual results, 2, manipulate the cut bill and examine the results, 3, calculate and report the yield from each trial, 4, record the number of cuts per board from each trial, and 5, observe and report effects on the nesting system. So for our simulation, we have considered 4 major steps in the manufacturing process. The first is generating the defective boards. We choose a number of boards to generate for the input, and our output is a set of disjoint intervals representative of the endpoints of defective areas, which considers overlapping defects. We use a zero-truncated Poisson distribution to model the number of defects per board and a normal distribution to model the locations of the defects. The second major step is applying the mandatory cuts, which we refer to as saw phase 1. Saw phase 1, our input, is the board's generator's disjoint intervals obtained from the first step, and the output is a list of irregular board lengths obtained from them after the mandatory cuts have been made, removing the defect. So this process is simply removing the defective intervals. The third step is applying the cut bill. We also refer to as saw phase 2. Our input is a list of irregular lengths obtained from saw phase 1, and our output is a list of allowable lengths obtained from implementing the cut bill on input lengths. So in detail, in this process, if the length is not in the cut bill, a helper function returns false. If the length is in the cut bill, it returns true. If true, it will place the length into our output array and move on to the next length. If the length is not in the cut bill, it will subtract the upper interval and check again if the difference is in the cut bill. If true, this will return 2 board lengths in the cut bill, one being the maximum length and the other being the difference of the initial board length and the upper interval. So this phase is where the yield is calculated from each cut bill trial, because after this phase, there's some more cuts, and therefore there's a more square foot loss.
The fourth step in the manufacturing process is the nesting system. The nesting system efficiently packs the short boards into what is called a lane. And 2 lanes equals 1 deck. The nesting system achieves this by using the probability of the next 500 boards and also a size restriction on lanes, where each lane that's built has to meet a minimum length of 47 inches and not exceed 60 inches. Our function takes the output from saw phase 2, which is that array of various lengths, and each element is then evaluated and a decision is made whether to drop a short board into a lane or not. That decision is based on the probability that a subsequent board in that array will complete the lane. This probability was initially determined by using the actual results from the manufacturer. They gave us a spreadsheet with over 1 million recorded board lengths, and using Excel, I partitioned the lengths into percentage buckets. The range was the shortest length in the spreadsheet that we consider was 8 inches, the maximum was 60. However, once the nesting algorithm that we've developed reached the 501st element in the input array, the probability is then calculated based on the remaining lengths from that input array. When adding a board to the lane in progress, so for example, when you're building a lane, you're going to add a board. If it meets that length requirement, minimum 47 inches, not exceeding the 60, then the lane is considered complete. However, if it exceeds the 60 inches, the nesting algorithm will then create a new lane. Once a lane is completed, it's then moved to our output array of completed lanes, and the function then moves on to evaluate the next board length in the input array. It's important that the nesting algorithm accurately models the actual nesting system used by the manufacturer, because any cut build that is implemented cannot cause a real nesting system to become backed up. This would cause the entire production line to shut down and be a considerable loss to the manufacturer. So in order to test the defects, in order to test the cut build trials, we're planning on using a fractional factorial design in order to test different cut builds. A fractional factorial design is a carefully chosen subset of a full experimental length. For example, suppose we've got 8 intervals to trial. For example, let's say we've got these 8 intervals and we're going to trial 4 at a time. If we were to do the full factorial run, that would be 64 simulations. However, if we choose 4 at a time, now you're doing this amount of simulations, which ends up being 16. So you save a considerable amount of time on the simulation runs, and you've got the yield results at the end there to compare the different companies.